Hey, I'm Eddington. I'd like to present our work about single-view 3D human pose estimation, named SRNet, improving generalization in 3D human pose estimation with a split-and-recombine approach. 3D human pose estimation is to estimate where are the 3D joints of the human body. For predicting 3D pose, we first estimate the 2D positions of key points from an image, and then lift them into 3D. Our method focuses on the second stage. One of the challenges for single-view based method is insufficient generation ability. When test poses have not been seen in the training set, it is really hard to predict promising locations. For instance, if we train a model on action greeting and test on sitting, those sitting poses will hard to predict well. Single-view 3D human pose estimation has obtained great improvements recent years, yet most methods may fail for unseen poses with limited training data, since the accuracy of this task depends on the diversity of data partially. Some works further augment the training set with more geometric poses to exchange some local parts between two training samples, to combine real and virtual camera views to get diverse viewpoints, to use mixture 2D images or synthetic poses to obtain more potential data. Those methods are orthogonal to our goal of robustly estimating rare and unseen poses. Our method is not to utilize more training data, but consider leveraging local joint and global joint relations better. Meanwhile, some recent works take advantages of physical connections that exist between body joints to improve feature learning and joint prediction. They naturally propose theoretical skeletal information path strategies to encode the kinematic structure, to set some anatomical constraints like same bone length among time serials, discarding physical embedded poses, and finally to explore the skeletal structure as a graph embedding way. For both theoretical and graph-based techniques, feature learning within a local group of joints can be heavily influenced by joint outside the group. But how to relieve the side effect of irrelevant joint efficiently? This work can give you some answers. In this work, our approach is based on the observation that rare poses at the global level can be split into local joint configurations that are usually less rare in the training set. For example, an unseen test pose may be predicted from the upper body of one training pose and the lower body of another. Before introducing our method, we start with the most common baseline for lifting 2D joints to 3D, and then describe how to modify those baselines to follow our strategy step by step. From a 2D to 3D pose network, the simple baseline is multiple fully connected layers with residual connections. Each intermediate feature and output joints are fully connected indiscriminately. It's allowing the prediction of an output joint to be overfitted to the positions of distant joints with less relevance. So we naturally partition the whole body into local pose regions, like many previous work. To accommodate this partitioning, the FCN layers are divided into groups as group-connected layers. However, a drawback of group-connected layers is that the status of other body parts is completely unknown when inferring the local pose. As a result, the set of local inference may not be globally coherent, leading to low performance. There is thus a need to account for global information while largely preserving local feature independence. To further keep local representationability and information passing with global coherence, three more baselines can be proposed. The first one is late fusion, which can learn local features in the earlier layers and fuse the local features by later fully connected layers to gain global information. The second method is early split, aiming to provide more expressive features for each group by cutting the connections between groups in the later layers. The final one is split-fuse-split, learn local features in the early stage and fuse them in the middle, then split them again for local inference. In a certain degree, those three baselines can enhance local representation abilities and keep global coherence, but they still not answer how to relieve the side effects of less relevant joint 3D. To address this problem, we propose to incorporate low-dimensional global context in a group-connected layer, which can costly preserve information from the less relevant joints by a dimension reduction way, and both keep strong local information. Thus, the split whole will feature into local parts, and recombine a low-dimension global context can balance feature learning dependency between the most related local region and the less related global context. The split and recombine strategy can be adapted to both single pose and temporal pose settings. Specifically, the group-connected operations for local joint groups are replaced with corresponding temporal convolutions for local feature learning, where the features from other joint groups undergo an extra convolution for dimension reduction in channels, and recombined back with the local joint group as global context. Compared with related works, our proposed method can enhance local features, keep information parsing with global coherence, local inference, and with dimension control to less relevant joints. Our approach is validated on two popular benchmark datasets. Human 3.6M consists of 3.6 million video frames from 4 camera viewpoints with 15 actions. We verify our method by 3 protocols. Subject protocol 1 and 2 are the standard protocol with all seen actions at cross-person test. Cross-action protocol means train on only one action, test on all actions. And our proposed rare pose protocol, which measures how the poses are not similar or rare to training samples. We take the top 10 and the top 20% as verification. Furthermore, we evaluate our method on MPI-NF 3D human pose test set to examine cross-dataset generation ability. Let's see some evaluation study results. All our evaluation studies are evaluated on the human 3.6M dataset. First, we compare the baseline network with our SRNet to verify the efficiency. Late fusion, early split, and the split fusion split baselines can surpass fully collected baseline, which indicates that local feature learning and local inference are each helpful. SRNet, with its use of low-dimension global context, performs significantly better than the SFS baseline. The improvement is especially large on rare poses, indicating the stronger generation ability to such poses. Second, we show how the low-dimensional global context can be brought back to the local group using a combination operator. We empirically evaluate the design choices of using addition, multiplication, and concatenation. It is shown that both addition and multiplication obtain favorable results, indicating their effectiveness in recombining the low-dimension global context. Thirdly, we present the performance of SRNet with different dimension h for the global context. When h is equal to 0, SRNet degenerates into the group-connected baseline. It can be seen that the group-connected baseline without any global context obtains the worst performance. This shows the importance of bringing global context back to local groups. Also, it found that a lower dimension of global context leads to better results. The best result is achieved by keeping only a single dimension for the global context. Fourth, we compare the results of using different numbers of local groups. More joint groups lead to the greater local correlation of joints within a group. It's shown that the performance first improves with more groups, especially in the rare pose case. However, with more than 5 groups, the performance drops due to the weakening of local features when there are fewer than 3 joints in a group. Moreover, to show that separation into local groups is important, we randomly shuffle the joints among a subset of groups. The right table shows that the performance decreases when randomly shuffling joints among more groups. This indicates a strong physical relationship among joints in a group is a prerequirement for learning effective local features. Next, we compare with the state-of-the-art in 3 different experiment settings. First is the single frame and temporal model on human 3.6M of protocol 1 and 2, both of the standard protocol. Our model surpasses the SOTA in each case. The second protocol is a cross-dataset test on MPI-NF 3D human pose. When only evaluating on its test set, it improves upon the state-of-the-art by a large margin, indicating superior generation ability. Finally, compare with the simple baseline and the state-of-the-art methods using the cross-action protocol by detected and ground truth 2D inputs. Specifically, the upper table shows that our method yields an overall improvement by a relative 12.2% improvement over the LCM method and perform better than 93% of the actions, indicating strong generation ability on unseen actions. For more results and analysis, please refer to our paper. Next, we show some qualitative results. From the previous table, we show the action of worst results, named sitting down, compared with the SOTA temporal model. We can see that our method can perform better under the most difficult action. Moreover, we choose some results on 20% rare pose samples randomly. And then, we present our cross-action test results. The first row demonstrates training samples, and the second row shows our results from the front and top view. When training on action 4, test on the action smoke. SRNet can generalize well on the cross-action settings. The same condition on the example of training on action discuss, test on direct. Lastly, we show some failure cases. When the body parts have totally unseen in the training stage, test results can be dramatically worse. For example, if training action is only working, then test the model on a quite different action setting. We can observe that the lower legs are usually predicted badly. We show the video 3D model and SR convolution results. Under those severe cases, our model can be more robust than the video 3D model, but both two models perform badly with errors over 1000 mm. More details can be found in our paper, and thanks for your watching.